just thinking out loud right now, but if we know that there is an elastic solid and these are all just wave shapes, maybe we can create new wave shapes. You know what I mean?
Yeah,
Maybe there's other kinds of wave modes we can create. Who
right.
knows?
What Bacon taught us is if you understand the nature of the underlying entities, you can now alter that nature in order to
Hmm.
produce new and desired effects.
Yeah,
So
exactly.
if we know the nature of the medium, then perhaps we can perturb it in new ways it's never been perturbed. And what
Yeah,
would that amount to? It'd
exactly.
be
That would
new
be so cool.
waves, also known as like new entities, basically, like new kinds of light, new kinds of matter. I'm not
Yeah.
saying that's definitely going to happen, but this is the kind of unthinkable things that happen when you identify new underlying entities.
Because you just have the
Nuclear.
formulas. How would you figure this out? If you had no picture, just black here, right? Just the formulas. I mean, I couldn't do it. I mean, I don't know how you can come up with new ideas if you don't have
Yeah,
any
I mean, it's
visualizations.
impossible. This is the second lecture in Chantal Roth's lecture series, The Mechanical Universe. If you haven't seen lecture one, then that's quite all right. This lecture will still make perfect sense to you. But if you'd like to see the rest of the lectures in her series, you can go to the description below and see a link to the entire playlist. In this second lecture, Chantal will explain her model of gravitation, of how she can explain gravitational forces, length contraction, duration alteration, all in terms of the variable density of a medium. Let's understand one more piece of how an ether hypothesis can tie everything in physics together here on Inductica.
If space indeed has properties, or if there's an ether, however you want to call it, what does it mean? What does it imply? So let's start with general relativity. What is curvature? And how do light waves bend towards massive objects? Let's check again what other people thought, in particular Newton. And I think it's pretty amazing that he wrote that in 1704, which is pretty amazing because he thought the universe was some kind of elastic solid too. And he talked about refraction. And he said, doth not the refraction of light proceed from the different density of this ethereal medium in different places? The light receding always from the rarer parts of the medium, and is not the density thereof less in free and open spaces, void of air and other grosser bodies? And then he said, is not this medium much denser within the dense bodies of the sun, stars, planets, and comets than in the empty celestial spaces between them? And though this decrease of density may at great distances be exceeding slow, yet is the elastic force of this medium be exceeding great, it may suffice to impel bodies from the rarer parts of the medium towards the denser with all that power which we call gravity. I think that sounds so cool.
Yeah, yeah. He had a very yes. That's the way they wrote back then.
It's funny, but it's like, oh my God, it sounds so important. And then the power which we call gravity. But think about it, he thought about that. It's so amazing, right? So he had the idea of refraction. So we really need to understand what refraction is. And I realized last time when I talked with Demystify Psi, there was some question about it. So I thought I want to spend some time and explain how refraction works because it's important that we understand that. And basically, it's all about Snell's law. So, okay, we all know how glasses work, right? When you wear glasses, you have light waves coming from the air, they enter glass, and glass has a different optical index, a refractive index. And so, based on that index, the light rays, so here is indicated one of those lines here is basically, you can call it a photon if you like, the light rays, they bend. And well, how does that really work? Why does the light ray bend? And the reason is now in a normal material, when you have a high refractive index, it means that the speed of the wave slows down. And I know people gonna go, objection, objection. Oh my God, how can you talk about speed of light? No, no, let's just talk about real materials for a moment. And then don't worry, it will all work out. So the reason is the speed of the wave slows down, and that's why you get this refraction. And we can also do this in a gradient. So there's some materials that
Mm.
yeah, when we change the angle, so we have now a gradient from top to bottom, and you can see how the light rays start to bend, right?
So just to help the audience out a little, at first we had a sudden alteration of density, which
Yes,
caused the direction of the wave to just alter suddenly. But here
yes,
we have a gradient alteration
mhm,
of density from top to bottom, and it
yes,
causes this gradual bending of the wave.
exactly. And it happens basically, you can imagine each step you have a little difference, right? Each step you have a little change.
Yeah.
Yes.
And do we have let's see, is the green the denser or
Oh, denser below. Here's another one. I use this one because it you can zoom in here to see, and we can
Mhm.
also stop it. So let's see, pause. And you can see that the wave phases, they still line up, but it just slows down as soon as it enters the other medium. So the bottom is
Mhm.
denser. The bottom
Yeah.
here is then the higher refractive index means also denser, basically.
Mhm.
Um,
And as Newton said, the wave shies away from the rarer areas and plunges
yeah,
deeper into the denser areas
yeah,
is the
yeah. That's a
general pattern.
well-known thing with waves. It's very well known, very well studied. Um,
Yeah.
so there's
My
really no mystery about that. But just,
yeah.
and again, I know there are going to be objections. So yes, I agree. Speed of light is constant, in fact, for all
We
observers.
we need to make a quick like addendum. The two-way speed of light is constant for all observers.
It's actually for all observers because I'm going to
No,
show
no,
that
yeah, it
later.
is for all observers, but it's the two-way speed because we don't know the one-way speed.
We can't
We
measure it. Yeah, we can't. The
Yeah,
thing is, we can't
we
measure
haven't
it.
measured it, and
Yeah.
in now in special relativity we presume that it's this that the one-way speed is the same for all observers, but that's a presumption. That's
Oh, yeah,
just a
I agree.
convention for
It has never been
getting the
measured.
right
Yes.
answer. Yeah, so it's I think it's important to note that when you say this, like this is a real objection, but we have to reframe it to be a valid objection. In my opinion, you can tell me if you disagree, but this should be reformulated as like the two-way speed of light is
Yes,
constant
that's
for all
true. The
observers.
two-way
Yeah,
speed of light is
yeah,
constant for all observers.
yeah,
Yes,
and that's
exactly.
there's no disputing that. That's
There's no
definitely
disputing
true.
that.
Yeah,
No, and we'll see. You might not believe it now. People who see refraction to speed of it will work out.
yeah.
Yes. So other examples of refraction. I don't know, maybe I'm going overboard with this, but I really want to make sure people understand this. This is an example of glasses even. Some glasses have like varying density, and it bends the light. This is a more traditional image of how refraction works, right? This is well studied. There's absolutely no mystery about it. There is even waves in the earth, okay? Shear waves in glacial tilt structure. And again, we see that equation here. The shear wave, the speed of the shear wave depends on the shear modulus, on the stiffness and the density. And you can even see that, in geological structures. So they get this kind of refraction even in earthly materials, basically.
Mhm. Yeah.
Be- There's also other effects in air. Like for instance,
Oh,
when
this is
when
cool.
when the air has different temperature, it changes the refractive index of air, and light can bounce off and even reflect. So you see these mirages, like in the desert or something. When you think the object is really, it looks like it's up in the sky, but actually it's down there. It's just because of there's colder air at the bottom and hotter air on top, for instance. That you can also do with sound. Sound also has refraction when you have warm air and cool air. Again, the speed of the wave changes. And it can happen that, when you have warm air at the bottom, cooler air on top, and you shout out that your sound waves are actually going up and say your dog can't hear you now.
Mm.
um, there also people have been using this called optical analogy of general relativity in optics. So they use this, for instance, to create meta optical black holes, basically. So they have this meta material where they layer different materials with different refractive indices, and they can create like optical black holes. And this is a real experiment. This is a real paper. real experiment. They show how the light wave starts to curve around this metamaterial. It looks like a black hole, and this
Hmm.
is the calculation. So, and there are also black holes of sound. So there are many
So let me
examples.
make sure I'm understanding these optical black holes. So what we have is we have some material that light's allowed to penetrate, but some one part of the material is such a high refractive index that the light, as Newton says, is going to bend into that. It's going to bend towards that higher refractive index. And the difference in refractive index is so great that the light bends into this region and doesn't come out.
Yeah, it doesn't even have to be so extreme. As long as you have a
Okay.
gradient, you make it slightly more higher and higher and higher refractive index, and based on that angle, right? You can, if depending on that angle, you can turn it into a curve, into a circle, basically, right?
Right.
You can just
Yeah.
make it doesn't
Yeah.
even have to be extreme, you know. Um, and there's some experiments you can even do in the kitchen. There's some YouTube videos. I haven't actually tried it myself, but I saw the YouTube video. So where
Mm.
you can do that with water. So you put water in a bowl and a lot of sugar, tons of sugar. That's like
Uh-huh.
kilograms of sugar.
Uh-huh.
Um, and you have to let it sit. Okay. So there's a gradient needs to form, sugar gradient. So you have a lot of sugar at the
Mm.
bottom. On the top, it should basically be just water. So don't stir. And then when you shine a laser through it, it starts to bend towards, the higher refractive index, which I think is pretty cool. I
That
mean,
is very cool.
yeah, right? That's pretty cool. So, of
Yeah.
course, I have some more video simulations. So here is a simple example. I basically created a gradient here in a 3D object. So I have in the middle, I have a higher refractive index than outside. And I'm
Mm.
just
Hmm.
calculating the light rays, how it would move through that, right? And based on that gradient, you can get all kinds of stuff, right? So this is one explanation, one example. Then I also have,
So once again, because we have denser material in the middle, the wave bends towards that denser material.
yeah, here's another one. Maybe I need to
And here
increase.
again with the same pattern.
We have a light ray that goes through. And so here I chose quite a high gradient. You can see in the middle, I think we have this. Does it say? Oh, yeah. You can also see the density where the light beam is, the index, the refractive index. It starts with 1 from the outside, it goes inside, and in here it was about 2 or 3 or something like that. So it's not that extreme. You get this curvature quite easily, actually. So here it's about, yeah, a little more than 1, depending on the angle, right?
Hmm.
Yeah. So this is now, some terms I'm using, because sometimes I'm using different words for similar things. So when I talk about refractive index, I mean, it really is exactly the ratio of the speed. So
Hmm.
the larger the index is, the slower the waves. You can imagine it's in your head, you can imagine it's just denser. More means denser. Sometimes I would say optical density, and it's really kind of the same word as refractive index, really it again the same thing. Now, of
Hmm.
course,
Hmm.
when we look at the formula, right, we have two things that could change. We could change the density of the medium, so the denser, the slower, or we can change the rigidity of the medium. So if we lower the stiffness, it will get slower. If we increase the stiffness, it gets faster. So how does that work with the metric tensor? So let's get a little bit more into general relativity. So
Hmm.
imagine in flat, I just call it flat space, right? There's no curvature, anything. We have just a flat, uniform, homogeneous cube. Let's say a cube of jello, you could imagine. Um, and then we are curving it. So what does that mean? Okay, so here we have this cube. And imagine we can now draw a grid on top of it, just so we have a way to figure out the coordinates, like where is something. And now what we can do, we can stretch it, right? So when we stretch it, for instance, you can see we use the same number of lines. So now it gets squeezed. It's no longer a square, right? It's now elongated in one way or the other. We can also curve it in one way or another, right? We can also add a static twist to it.
Hmm.
Now, if I tell you, if I give you this cube without lines, right? And I told you, can you help me draw those lines? You're gonna have a problem. You're gonna have to figure out, well, how many centimeters do I have to go, right? You need to tell me something. You need to tell me how much did you stretch it? How much did you bend it? Because otherwise you don't know, how to draw it basically. So this is what we see down here. This is the three-dimensional metric tensor. Of course, we'll have to talk about four dimensions, but first the three-dimensional. So if we start again from scratch, if it's just all the same size, all flat, it's all one. And these on the diagonals are how much we stretch it. So when I stretch it, you can see how this number changes here. We changed the x direction, and then we stretch it in the y direction, and we stretch it in the z direction. So this number tells you how much longer it will be, or how much shorter.
Yeah,
So
the deformation along any given axis.
Exactly, the deformation. And then these diagonals.
It's just the stretch or squish along any one axis, because there's other kinds of deformations as well.
Yeah, like the diagonals, right? So if I do this, you can see the diagonals start to change. You get this
the off diagonals.
Yeah, exactly. Because the angles now change. Like before, the angles were still right angles, right? Before they were still all right angles here. I'm just changing. I'm not curving anything. I'm just changing the length. But here I'm starting to twist. And now it gets more complicated, because now it's not, you can't even use right angles anymore. You have to know, well, how much do I have to change the angle when you want to draw the lines? And that's basically what it is, right? So imagine you had this, if I do this here, imagine I print this out 1,000 times, and I print a sticky note with these numbers on it on every, and on many different places. So, and we have this probe here, right? This red thing is the probe. So you can see how it changes. As I move that probe, because in different places you will have slightly different numbers depending on how much it's curved here or there. So you can imagine we put those numbers in different places all over this cello, and then when you're here, you can then look up the number. Well, how much do I have to go to the right? Oh, I need to multiply by 1.06 in x direction. I need to multiply with 1.07, and so you know where the next line is basically. So that's basically, I mean, that's what the metric tensor is.
Now let me, so let's get clear on this. So you're proposing that the metric tensor is not the curvature of space and time, but rather the curvature of some entity. It's just literally the bending of some entity, some ether entity. And what is that ether entity? It's the entity which carries the electric and magnetic field.
Yeah.
And so as a result, light will bend along with the bending of this entity. And that's gravitational lensing. And then matter waves will change and matter waves will change their course or bend along with the bending of this medium. Because matter waves, quantum matter waves, we have found out that matter is a wave in the ether. So or rather, matter is a wave, so it must be a wave in the ether.
Yes.
And so why are planets and their courses changed by matter? Well, because matter bends the nearby medium and causes other matter to change its course as a result.
Yeah, and we'll talk a lot more about that.
That's what you're trying to visualize for us here. What's that?
Exactly.
Yeah.
That's basically it. Yeah.
Okay, now I'm going to bring up an objection that people often raise when they see this kind of thing.
Okay.
And this is a little, I regard this as a little bit of a stupid objection, actually, but it's, I shouldn't say stupid, because it's a flawed objection. I don't want to insult the people who say this.
No, we shouldn't do that.
They're not being stupid, but they are making a mistake. It's a flaw. So, okay, here's the objection. In general relativity, it's not a bending of space. It's a bending of space-time.
Oh, next slide. I'm actually, this is
okay. Well, there we go. Yeah,
you can't see because
then
it's literally. I should have put the objection slide. I was thinking about adding an objection slide, but
I mean,
see, what about
I brought up the objection, and here we go. So here's the answer. And
That is
I'm
so
going to bring up
important.
why I think this is actually a wrong-headed objection, but
Oh,
we're
I'll,
still
I'll
going
I'll
to
have
answer
several
it.
slides on this alone because
Yeah.
it's so important. And even when I talked to, I think, the Mystify side, there was some confusion about it. It's
Okay.
really important to understand what is a clock. And they have different types of clock. We have clocks that are somewhere in this cello, right? There's a clock here, there's another clock. They're different clocks. These are called coordinate clocks. Then we have clocks that move along with some object inside the universe. And we see how that clock, that's another kind of clock. Now, of course, we're kind of sitting outside this toy universe and we watch what's happening, right? I'm going to call this our lab clock or absolute clock. Of course, you can simulate that in a way. Imagine someone is sitting far away from anything that's happening in that, gravitational area, far away. That's similar. Like we are basically our clocks always in an area where there's no curvature. It's all good, right? There's nothing happening. So, but
Yeah.
what is a
We're going to
clock?
imagine a clock which is not altered by the ether, basically. We're gonna, is that what you're saying? Like it's not a clock that's like, you're saying it's like outside the universe, but that's kind of a silly thing to say, but it's more like just,
It can just be far
you know,
away, but imagine it's just far away. That's also okay.
yeah,
Like,
right. It's not influenced by the things that are influencing
but
this
we're
here
watching, we're
clock.
watching some, we're observing something, and we're just far away, right? And I want to
Yeah.
get into, if we're saying there's this clock, it's far away, then we get all into this question about simultaneity and all. Let's just say
Uh-huh.
we're simulating. If you write a program to simulate the universe, we have a computer clock. We can just use that. It's fine. Like we
Okay.
watch what happens, right? So now there are different kinds of clocks. Now imagine maybe the easiest one is a circular. Imagine we had this clock that's just like a fiber optic strand. It's just a light wave going in circles.
Hmm.
And this is going to be our clock. So we call that, when it's once around one, we call that 1 lap second, whatever, 1 second, we call that 2 seconds. We can also call it something else. So our clock is a light clock. And I think you can see where this is going. We can also, of course, have a clock that, sometimes people use these mirrors. So we have a laser beam and a mirror, and it's reflected, right? And we have a detector down here. So whenever the light beam comes back, that's 1 unit of time. We call that one. And then we have two and three and so on. Okay. And this is important. Now, of course, I can see the objection already. You might say, well, but my watch, I have an analog clock. That's not light-based, right? So how can you use that analogy? Well, the thing is, again, when we zoom into any mechanical clock, even deep down, deep down, we have atoms and electrons, and these are wave-based. So ultimately, we do end up with waves again. So that's the whole point. But of course, it's easier to imagine to have a light clock because you can imagine if the speed of the light changes, what happens to the clock, right? What happens if I slow down the light wave? Well, then our clock is going to tick more slowly,
Yeah.
right? So, what about time? Because so now I have, of course, we have to look. The real metric channel is four-dimensional. We have this other extra dimension we haven't talked about yet, and that's the time dimension. So imagine this blue thing here is our lab clock, and I even have like a version with the light clock, so it's even more obvious. So this clock means it's far away. It's the same density or whatever, the same. It's flat space time basically. We're flat space time. So, and if you don't do anything to this region of space, they tick at the same rate, right? They have the exact same speed. That's all good. But
Hmm.
now, if we start to change that property, if we start to
Mm.
change the density, the refractive index, so let's just, squeeze it a little.
Hmm.
And then, oh, look. And what happens, right? We change the refractive index. So what happens when we change the refractive index? We know refractive index is all about speed of light. We slowed the speed of light.
Hmm.
Viewed from the outside, again, really important. It does not mean these people, if there are people in this elastic solid here, they would never know. They don't know. They
And
have
why
their
not?
clocks. To them, it's just one tick after the other. They couldn't tell because everything is slowed down. Of course,
Yeah,
we from the
they're slowed down by
outside.
their clocks are slowed by the ether just as much as this purple clock is. So when they
Yeah,
watch it, it's ticking the same rate as it always was
of
because
course
their
they couldn't
clocks are
know. They
slowed as
have
well.
nothing to compare it against, right? They have
Yeah.
nothing. to compare it against. And this is what this extra four-dimensional thing is. It just tells us how much slower is the clock. That's all it
Yeah.
is. There's no
So it's
magic.
yeah. So my way of thinking about this is it's not like space and time are this abstract or magic space time. There is
Yeah,
no space time. It isn't this magic four dimension. This I shouldn't say magic because it's a little insulting against the people who think this, but like it's not this new unprecedented kind of existent that's a four-dimensional object. That's not what it is. It's a
yeah,
three-dimensional object that can be deformed in normal three-dimensional ways. But then on top of that, alterations to the object cause alterations in the rate at which things change.
yes,
And when
exactly.
things change more slowly, that is what people are talking about by time dilation. So it's not that
Yeah,
time and it so happens that you can produce this weird like four-dimensional geometry theory that accounts for the changes in spatial relationships and the changes in temporal relationships. And you can treat it as one big four-dimensional block that like deforms and stuff. But there's no evidence that such an unprecedented phenomena exists other than the fact that the math works. You can
yeah, and
get
of
the
course.
math to work also with this picture, where we
Mhm.
simply say, oh, when the ether changes, it changes the distances between things, and then also it changes the rate at which processes transpire. And
Exactly.
that is what you're
Yes.
calling time dilation.
It's exactly what you're saying. And just because people call it four-dimensional, of course, when I like when you write a computer program, in the program, I'm gonna have this call something called like a matrix or array, whatever. Sure, I have four entries because I have four entries. I can call it four-dimensional, but that doesn't mean anything. It's just convenient to calculate something to call it four-dimensional, but it's just bookkeeping. That's all it is. Like I can put a sticky note again everywhere, and then this number would just tell you how much slower everything is. And as
Yep.
you were saying, it's all the processes because speed of light is just, it it's not just the speed of light that's slower, it's all the processes are slower. Everything, mechanical clocks,
Yeah.
vibrations, because nothing can be faster than the speed of light. And that it totally makes sense because later, as we will see, if we consider matter as being waves as well, and light as being pure waves, it makes sense. Obviously, no wave can be faster than the speed of wave, right? So,
Yeah. And so the fact that time itself seems to be changing, that doesn't mean that time itself is changing because there is no time itself. There's just
yeah,
entities changing at
yes,
different
I
rates. And if
agree. Mhm.
entities change at a slower
Yeah,
rate, that is what you're calling time going
yeah.
slower. But
Exactly. That's all it
yeah.
is. And then and funny thing is people always object when I mention something like this, oh, inside close to a large object, time, the speed of light slows down and they will object. But the thing is, even in science fiction movies, right, when you would if you were watching a rocket say pass a black hole, and let's say they had a beam of light and you were watching this from far away, how they go close to a black hole, that beam of light for us would look slower. So while locally my speed of light is always the same, I cannot detect any difference. But if I were to watch their flashlight, how it would move
Mm,
when they're close to a black hole, we would see everything slow down. The rocket would slow down, the people would slow down, the clocks slow down, and we would see their beam of light slow down. They wouldn't notice. So for them, their speed of light is always the same. And for us, our speed of light is the same. But when we watch a rocket pass, close to a black hole, everything would look slowed down, including the light beam.
yeah.
Like we
So
do
and,
here, right? Yeah.
it's just like what we're seeing here. Yeah.
Exactly.
The
Yeah.
blue
Yeah.
clock is not altered, and so from its point of view, the purple clock is, well, in this case, it's oh yeah, it's slower. The purple clock is slower.
Yes.
Um, and but if you put a purple clock in this same deformed ether, then it would also be slower. So from the perspective of that purple clock, from the perspective of any clock inside the blue jello, all the clocks are the same because they're all altered by the same amount by
Yes,
the ether.
exactly. All the clocks in the nearby. Well, if we move a little away, right, then you will see it will change a little bit. So we change the position to some other area. Maybe there's a little less curvature, then it would slowly change. But yeah, then the clocks nearby are all the same, so they wouldn't be able to tell.
Yeah. We don't know. Something I just want to bring up is
Okay. Hmm.
the fact that all physical processes are slowed by these gravitational effects gives rise to a reasonable hypothesis that all physical changes are actually some kind of wave phenomena
Yeah.
in the same medium, because
Yes.
all of
Makes
these
sense.
changes
Hmm.
appear to be altered by changes in the medium in the same way,
Yeah. Exactly.
which makes people think time itself is changing, but time itself isn't a thing. There's just the
Yeah.
changes of things.
Yes.
And it appears as though processes, all processes of change go slower as a
Hmm.
result of these alterations in the ether. What would be nice is if we figured out some particular process of change that was
Yeah.
not changed by this. That would be a difference that makes a difference.
Totally agree.
But
Yes, I
so
totally
so
agree.
far it
Makes sense.
doesn't. Yeah, but so far it doesn't look. I don't think there's much evidence for that, since all physical phenomena appear to be of this medium, which makes
Yes.
it tough because there's nothing to compare it against.
Yeah.
People make the analogy it's like a fish trying to figure out that he lives in water, but it's far worse than that.
It's
The
worse than that. The
dramatic.
fish is made of sound waves. It's like
Yes, exactly. Yeah.
the
It's
fish
like
is
the
made of
fish is
sound
made of
waves. His
water.
clocks are made of sound waves. His
Yeah.
measuring sticks are made of sound waves. What's the poor fish
Yeah.
gonna do, you know? I mean, we should think about. I think the thing is, once people start to think about, maybe we can come up with simulations. Maybe who knows? Maybe there's a way. I don't know to do something, but
But we this is how we do it. We're noticing it. We're noticing it because of, let's see, differences between the rates of change. But in
yeah,
order to understand the nature of that thing, we can't treat time itself as this dimension. We have to understand that time is just like a measure of change. And so we
I
have
totally
different
agree.
things
100%. Yes.
changing at different
Mhm.
rates
Yeah.
depending on how the ether affects them. So even
Yeah.
though we do face this enormous challenge where we are like the fish that's made of water, we're starting to notice there's a way to get to this.
Hmm.
It's challenging, but there's a way to dig into these facts with the right philosophy and the right kind of
Hmm.
thinking about these
Yeah.
phenomena.
Exactly. Exactly. Yeah, we just talked about this. So yeah, what slows is the mechanical clock speed. So regions with higher optical density will result in slower light waves, hence slower clocks. And of course, we'll talk about this a bit later also. So the mass energy. So somehow, when you have a region with more mass, more waves, more transverse waves, more standing waves, more matter, it changes the property a little bit of the elastic solid. It changes the density,
Mhm.
makes it a little bit denser, a little less stiff. So that's how matter can actually change the local speed of light. And
Mhm.
I do have another, I think, simulation here, a short, an easy one. This one is, oh, I'm just sending a light beam through this elastic solid, I guess, and then now I am creating a gravitational well inside again in the middle. So we can see what happens to the beam of light as I increase it. And you can also see how the clock slows down. So the speed of light is now a lot slower already. We can do, maybe we can remove the grid.
You can get it to loop in on itself
So we can
completely.
see, and you can get, this is basically in a black hole, right? At this point.
Yeah, cool.
And it's
Cool.
just refraction. All I'm doing is it's, and you can see how the clock is now almost not at zero, but it's very slow now. I mean, this is
So
not exactly in the center. So
so that's actually very remarkable. A lot of people when they think of light getting absorbed by a black, yeah, zoom in on this. This is something to ponder. When people consider light getting sucked into a black hole, as we see here, people are, I don't know about you, but the image that was always in my head as a kid was that like the light just gets destroyed. Like it's nowhere now. The light is just annihilated by the black. And it's true, like if you got sucked in, you'd get spaghettified, you'd get
yeah,
like torn limb from limb, so you would be killed. But the light that doesn't happen to the light. Instead, what happens to it?
it spirals inside the black hole. It spirals in like this. It's still
Yeah.
there, maybe. I mean, I
It's
don't
probably
know. We
going in
can't see
circles.
inside.
Yeah, exactly. I
It's just
mean,
spiraling. It could be that it's just spiraling inside. And why can't you see it anymore? Well, because it's a freaking black hole. No light's allowed to escape because any light that goes in just spirals around inside. And so it's
yeah.
not that it's like annihilated, it spirals around inside.
And also, it tells you a black hole doesn't have to be a singularity in that sense. It just, the
Hmm.
refractive index is not even that extreme. I mean, you can create them in the lab, the optical black holes. So it doesn't have
Yeah.
to be zero dimension. I don't know exactly how large it is. I think for the sun, it would have to be like this 2 kilometers or something. I don't know exactly, but you can calculate, the size it would have to be for it to be a black hole. So these objects don't have to be so mysterious. It's just that the refractive index, the gradient is large enough so that, it keeps bending light and, it doesn't have to be infinitely dense, and all that.
Yeah.
So, I mean, yeah. Yeah.
It just
Uh,
has to be dense enough to make it so light can't escape.
yeah, exactly. Oh, this is the same one. I've shown this one already. Okay, and then of course now some interesting questions or observations that we know of. So, so on the left side here we have a high refractive index. Let's say on the right we have a low refractive index. So, what happens is that when light comes in, or when light comes in from the right from space into say a black hole, right, or in even just the sun or just something that's high refractive index, it will appear blue shifted. And on the other hand, when the light wave goes out, it will appear red shifted. That's all the same thing. It's all the same logic. So I think, let's see, light pulse, animation speed, they're emit pulse. So when we have the left side is near a mass, a large mass, here the light speed is slow. We have a high refractive index. And when the light moves out towards, space, empty space where space-time is flat, um, it will first of all get elongated. So you see it will be redshifted. So when the light arrives outside far away, it will look redshifted. And on the other hand, when we do the other way around, light that comes in, it will get squeezed. As you can see here, right? It will get squeezed. The frequency will look shorter. It will look like it's blue shifted from someone who measures the beam of light here close to a massive object. And it's the same thing again. It's just refraction. That's all it is. It's pretty simple, right?
Yeah, right, right. Yeah.
I mean,
Uh,
I'm sorry, it's amazing. And then, Newton thought about this in 1704, like 300 years ago. Why can't we figure this out? I mean, shouldn't we look at this more?
yeah, I mean, well, the answer to that question is bad philosophy. Why can't we figure this out? It's bad philosophy. Like philosophy has our way of approaching the world has degraded since Newton. Where Newton was looking for physical cause and effect relationships, and now we aren't. So that's why, and that's the role in history we have. You and me and the other Pamo people is we are reintroducing the right way of thinking about physics, about identifying cause and effect relationships of entities acting on one another. Why does it redshift? Well, because it's going into a rarer medium, which is the way any wave works.
Yeah, exactly. Yeah,
Yeah.
it's pretty simple, right? I want to, my hope is to make it so trivial that people will like go, duh, what are you talking about? It's obvious. When I
Yeah.
talk to my kids about this, they're like, Mom, what's the problem? It's obvious.
Yeah, when I teach electromagnetics,
Mhm.
I introduced the ether very early. As soon as
Oh,
I start
okay.
talking about when I taught electromagnetism in college, I as soon as I introduced the concept of an electric field, I introduced the concept of the ether. Now,
Mhm.
at first, I introduced the concept as a hypothesis.
Yeah.
I say, I'm convinced of this, but based on what I've taught you so far, just treat this as a hypothesis. I haven't
Mm.
given you enough information to be certain of this, but you can see that it makes sense. What if this field is the action of some medium at each location.
Yeah,
And I keep
exactly.
saying that. And then when I get to the end, we start talking about electromagnetic waves. And then at that point, that's where I say, okay, this is what shows you that there really is a medium. It's not just a
Yeah,
hypothesis
yeah,
because each
exactly.
part acts on each other part. And that's how you know there's an actual medium. And then at the end, I will say, now, no one thinks there's an ether. I'm pretty much the only one. I mean, this is before I met the Pamo people. So I
Hmm.
said, like, I'm pretty much the only one who actually thinks there's a medium. And everyone in the class is just scandalized. They're just like, what? Like, well, and they're just like mouths are open, and there's like, well, what do they think is going on? And
Yeah,
like, like,
exactly.
what do they think is happening? Because it's like as soon as you introduce it this way, it's so natural to just think, yeah, okay, these fields are the action of some actual entity or medium. And once you tell them, like, oh yeah, we gave up on that, they just it's unthinkable.
You sound thinkable, absolutely. Yeah. Yeah, yeah. So out of curiosity, I was just wondering what gravitational waves look like, and I have read some
Mm,
stuff online where it seems to be some kind of also some kind of shear deformation, and it's
mm.
just for fun. And I was just wondering what would it look like, in the elastic solid, and this is what it will look like. Let's see. I have to change it to gravitational.
Whoa.
It's kind of cool, right? I mean,
Yeah.
I was just visualizing all that stuff. It's a lot of fun. I'm having a lot of fun with that. Just
Now tell us why it looks this way. This is what kind of deformations are we looking at here? It looks like we have some shearing,
yeah, it's
but
all
at the
shear.
same
It's
time,
just like if you look at the transverse wave, a transverse wave is just up and down, right? Or side to
mhm.
side, right? So all the displacement, I would call it, is going either up or down.
And
Then you
this
also
is all shearing. This is
all
all
shearing.
shearing.
Yeah, yeah.
Each
Because
layer
longitudinal,
moving like this
yeah,
with respect to each other layer.
longitudinal, so sound waves that we have in air, they would go like this. These are called longitudinal waves. There's no
Hmm.
shearing in this case.
So this is all expansion and compression.
Exactly. Yeah.
Yeah.
Then we also have
Okay.
circular waves. So
Okay,
circular
so
waves
this is
are
cool.
transverse, but they go in, the shear move.
So
It's in
this
a
is
circle.
shearing where the shear is in a it's circular shearing,
Exactly.
basically. Yeah.
Yes.
And the direction of propagation. Now, what's interesting about this is the direction of propagation is still at a right angle to the direction of both of the shears.
Yeah, I think so.
So you have shears in the, let's call it the XY plane, and then the wave, holy moly. And then, oh, that's really cool. And then,
Poles. Yeah.
so,
There's a
okay, yeah, that's
pulse.
and that's an up down transverse shear
Yes,
deformation.
yeah, and
Yeah.
long. Yeah, we can also do long. It's cool. I just these simulations again. They're all free. You can have them. I have no. You see the code too. You can change the code.
Hmm.
Yeah,
Yeah.
yeah. And they're actually. Oh, I know this is a bit off topic, but they're also optical angular modes that are a little bit interesting. They are.
Optical angular modes. That's really cool. Okay.
They have. Yeah. See, it's these waves exist. They use this diffraction grating that has like a fork in it, and then you get a light beam that has like it looks like a ring, like a donut shape. So the center is dark, and you have a light ring. And this is what it looks like if you did this in an elastic medium. This is the deformation. It would be pretty cool. I think it's pretty nice. So yeah, and these are gravitational waves. So again, shear. It's just the movement is a little bit different, right? That's all it
So it
is, but
looks
it's
like
all shear.
we have both shearing and
It's just shear.
compression along the XY direction, it looks like. Oh, it's just
Yeah,
shearing and that's
yeah,
it?
it's just shear. It's pure shear. I think. I'm not 100%
It
certain.
looks like there's compression in there. Like the layers are clearly shearing with respect to one another because you're if you look at it straight on, like look at it down the Z direction. Um, yeah, there we go. So let's look at just the first layer that's looking at us head on. We can see that it clearly is shearing. Like the layers are clear, like the layers along the X direction, let's call it, are like shearing with respect to one another. But then in addition, you can see it smashing. Like Like here, the X
Yeah, I
direction
see what
is
you mean.
long, and then that's the sound it makes. Then the X direction is short. You see, so it's both shearing and compressing along the XY
Yeah.
direction, and then the wave propagates along the Z direction. That's what we're so there we go, and it's propagating in the Z direction. But the deformations, that's
It's
I'm like
it's
making a
cool, right?
sound.
I mean,
The
the thing is, if
deformations are along the XY direction.
the
Yeah.
thing is, I'm just thinking out loud right now, but if we
Mhm.
know that there is an elastic solid and these are all just wave shapes, maybe we can create new wave shapes. You know what I mean?
Yeah.
Maybe
Yeah.
maybe with light, who knows, we can engineer something with new kinds of like these OAM waves. Maybe there's other kinds of wave modes we can create. Who
Right.
knows?
And yeah, and if you understood the nature of the medium, you could inspire in it, perhaps you could inspire in it new kinds of way. I mean, I'm just repeating what you said, but
Yeah, yeah.
like but I'll say it with a philosophical perspective here. What Bacon taught us is if you understand the nature of the underlying entities, you can now alter that nature in order to
Hmm.
produce new and desired effects.
Yeah,
So
exactly.
if we know the nature of the medium, then perhaps we can perturb it in new ways it's never been perturbed. And what
Yeah,
would that amount to? It'd
exactly.
be
That would
new
be so cool.
waves, also known as like new entities, basically, like new kinds of light, new kinds of matter. I'm not
Yeah,
saying that's definitely going to happen, but this is the kind of unthinkable things that happen when you identify new underlying entities. You can now
yeah,
manipulate them
exactly.
in ways that to produce effects you could never imagine before, just like
Exactly, because
with
you just have the
nuclear.
formulas. How would you figure this out? If you had no picture, just black here, right? Just the formulas. I mean, I couldn't do it. I mean, I don't know how you can come up with new ideas if you don't have any
Yeah,
any
I mean, it's
visualizations.
impossible. It's like trying to invent a nuclear bomb before. Well, let's not use that as an example, but like it's like trying to invent nuclear power before you know that atoms exist. You'd
Yeah,
never
yeah,
be able to do it.
exactly.
You're not aware of the thing you're getting the energy from.
Exactly, exactly. So of course, one question that comes up right away is, well, what about mass? What is mass? And I won't go too much into detail. Okay, I want to keep this high level, but still, just so we can think about what does it mean to have mass. And we haven't talked about matter waves or anything yet. But imagine we are looking into this grid, and we're just marking one grid point, one lattice point, and we see how it moves. This red thing. Maybe we can just make it larger. And if we ask the question about what kind of energies do we have in here, right? So if you just follow this one dot here as it moves up and then it moves down, it looks like a pendulum. Um,
Mm.
so you can immediately see, well, we have kinetic energy, right? Here it's fast and then it stops and then reverses here. It looks just like a pendulum. So we have kinetic energy. The movement of the elastic itself has energy. Then we can imagine we also have compression. If you compress a piece of rubber, it wants to decompress, right? If you let go, it will decompress. So we have compression energy, and then we have twist energy. When you have a rubber, again, you could twist it, and that's also kind of energy, right? So in that sense, if we regard matter as waves in this elastic solid, then what we call mass is just basically the energy contained in that volume. So imagine we have a volume of space, and here we have some matter waves. If we just do the integral, so we just sum up all the energies in there, all the twist energy, all the compression energy, the kinetic energy, all that together is the whole energy contained in that volume. That's basically what we call mass. And it kind of makes sense to see that in that picture, at least, that energy and mass is really equivalent because um, it's just, you have more mass, you have more energy, right? And
Now, now, well, so I have a question. What we're looking at here. So the idea is that matter is actually the motion of the medium. Is it's some kind of motion in the medium? Is that what you're
well, it's a
saying?
wave. I would be careful with
So
motion.
we
It's
don't
a
want to say motion, right? So
Yeah,
I was about to like layer something on top of that. And by
it's
motion here, I'm just being metaphorical.
it's a
Maybe we
wave.
could say this.
Yeah,
Maybe we could say this. Matter is the matter is the oscillation of some kind of property in the medium. Perhaps
yeah,
is that.
yeah,
So always looking for ways of expressing ourselves, which capture as many
Mhm.
facts as we can be certain of
Yes.
and no further than that. Or, well, actually, I mean, we're not certain of this, but we want to make hypotheses which presume the smallest number of
Yes.
assumptions possible
Exactly. Yeah,
in place.
totally agree.
Yeah,
Absolutely. Absolutely. Yeah.
yeah.
And so this, of course, matter is localized in space. So the wave has to go around in circles some way, right? Some way it's a standing
Mm,
wave or circular. And we'll talk more about the
yeah.
electron later. There's some circular components for sure because of spin and all that. It could be, and then of course the details have to be worked out, right? Is it a soliton wave? What exactly does it look like? But in general, it's what we call a particle is basically wave that's confined in some particular volume that we can localize in some way. So it's not a photon is a light wave that just goes through. It's just transverse wave. But if you imagine it going in circles, then you could turn this into a particle in quotes. And I have some more material on that later too. So so of course we talked about, I think people can understand how light works and how refraction works with light. But again, what about matter? And this is actually something that's also well studied in materials. So when you have, and this is a very huge simplification. It's just a wave going in circles. Okay, that's all it is, a spiral wave. But I added a index of refractive index here. So I think the left has a higher index than the right. And
Mm.
over time, because this wave is going in circles, it will start to slowly drift to the left, to the high refractive,
Oh.
because it's, yeah, of course. And it doesn't even matter what kind of wave it, like, exactly, is it a spiral or is it, the fact is it's going around somewhere. It's not a static thing. It's the wave is going in circles in some way, and that
Uh-huh.
alone is enough to make it move towards the high refractive index. And that's how you get attraction. That's how
This might be gravity.
yeah, exactly, yeah.
Wow.
Just
Wow.
refraction, and it's well studied. Again, it's nothing weird or magical. It's studied in materials. So the question, of course, is, well, how does matter bend space? And again, I won't go too much into detail because there's a paper, and we can maybe have a deep dive on this at some point. But basically, there's also this elastic optical analogy. So all we have to do is, as soon as we change the density or the stiffness, we will change the speed of light. So we have already talked about that matter is basically, you can imagine, as a packet of standing waves somehow. And imagine if this was, if space was like rubber and you start to twist it because you have these shear waves, right? You start to twist it. Well, then that tension will contract that rubber locally a little bit, which
Hmm.
means it has a slightly increased density. So because the same, medium mass packed in a smaller volume, when you twist the rubber, it will contract. And I think, do I have a simulation? I have some links here. I don't
Wow.
remember
Yeah.
what I did here. Oh, that's that one again. Well,
Well,
basically, it's just saying that, we need to change. If we change either the density or if we change the stiffness, we'll automatically change the refractive index. Um,
so this is interesting, Chantal, because now it seems like now you're actually implicitly committing yourself to the idea that these oscillations are indeed oscillations of not of just some property we know not what, but oscillations
mhm.
of the location of the parts. Because if the
Yeah.
parts get displaced, as you're saying, in certain ways, if the parts get displaced in certain ways, that leads to a higher density of the medium
Yes.
around that deformation. So that's actual evidence that there's a real deformation. It's not just an alteration of some property of the
Yeah, that's
medium,
right.
it's an
Yeah.
actual deformation.
Yes. Yes, you're right.
That's interesting. Now we still don't know, but it's certainly we're just noticing that it fits. If it is a literal deformation, it fits with this aspect
Yeah.
of how does matter cause gravitation.
And there's a paper, of course, we can again do another deep dive at some point. So he wrote this paper, Robert Close, a classical wave model of quasi-static general relativity. He
Hmm.
describes all the math and the details how this works. So basically, the rubber, if he uses actually the rubber band analogy too. Um, and there are experiments in solids that show that when you have this kind of compression in a solid, it actually also changes. The medium becomes a little bit softer. So we're not just changing density, we're also changing the stiffness at the same time a little bit. So he does all the calculations, right, in detail to make sure it all works out. So it's a combination of higher density and reduced stiffness. And this is a known thing. I didn't even know. Steinberg, Cochrane, this is a known thing. This is what it looks like. So when you change the density, it also changes the stiffness, basically, in relation to the density change.
Right. Okay. So it identifies. So basically, let's see. The higher you make the density,
The less
the
stiff it
lower
gets.
the stiff it has to
Yes.
be.
Yes, it can lower stiffness, and then as a result, you get, both. So both things change. The density changes and also the stiffness changes.
Yeah.
But yeah, so if anyone wants to know more details, Robert Close has worked this all out. Yeah, I think that's pretty much what I want to say about that. And of course, another question is, what about inertia and gravity? Here again, Robert Close wrote about this in detail. And it's basically, the particle, the momentum, and energy is defined by the wave property. And if you want to change the velocity of this thing, this wave that's in the medium here, in some volume, we have to distort the existing strain pattern. We have to add extra shear to get it moving. And the factor of the mass basically measures how much resistance there is to that. Because, the more you have of this matter, the more waves you have, well, the more you're going to have to change this pattern. So it's proportional basically to the mass. And in gravity, we have the same thing. We have the presence of matter. So again, the amount of energy changes the property to change the refractive index, right? Again, it's proportional to that amount of mass, the amount of matter you have. So again, it's the same. Like M is basically a factor, a proportionality factor, how much resistance there is. And in both cases, you use the same mass and it's the same acceleration. So, but he describes it in more detail if anyone wants to know how it works out mathematically. But yeah, I mean, that would explain it, why you have, it's always the same thing. It's just matter is basically waves in a certain volume. And if you want to change it, you have to change the wave pattern, the strain pattern. It's proportional to mass. And at the same time, the more mass you have, the more you change the property of that medium, the more you change the density and the stiffness, which then determines, the refractive index and the speed of light. So in summary, we can say that based on what we have done so far, we can see that space behaves like an elastic solid, that the refractive index corresponds actually literally to the gravitational potential. And I do have a simulation on it. It takes a moment to load, I think, because it's doing quite a few calculations. The time is mechanical. It's linked to the speed of light. And actually, the one person who really started this whole discussion is Hagen Kleinert. He had a paper entitled The World Crystal. He originally showed that the Minkowski spacetime is mathematically equivalent to such a model. And that's then when, Ilya, I don't know if you know Ilya Schmelzer.
No.
He has worked on this too. He wrote some papers on this years ago. The thing is, his paper is really hard to read. It's so full of math. I don't think there's like two people on the planet who understand it, but literally. And then Robert Close, he started work on this, and then also actually all of these used Hagen Kleinert's initial, motivation basically to do that. Oh yeah, here's some examples here's the sun mass as a black hole. Let's see. I need to click. See, I don't see because my camera is in the way. Here, if the sun were 2 kilometers wide, this is what it would look like. I just think it looks kind of nice. And then we have here, let's see, I think I can make it smaller so we can see the bottom better. Here's the typical gravitational potential, right? That's normally how it's drawn. So in the center, it's deeper. Then here we have the escape velocity, and this is basically like a black hole. So here you have 300,000 kilometers. So as you get up closer, here you would need more than the speed of light to escape. So it's a black hole. And here also you have the index. Here's at the bottom here, you have the refractive index, which follows the gravitational potential. So it's just inverted. So basically, where we have a low gravitational potential, we have a higher refractive index. But you can see it follows the curve exactly. Another interesting thing is the gradient of this is acceleration. So I think this one, yeah, the green line is acceleration. So you can see, closer to the surface, closer to that object here, you have higher and higher acceleration. And as you get to the center, it's zero, right? Because at the center, you're basically weightless. But the interesting, also, what's important though, time still runs slower in the center, even though there's no acceleration. So that's an important point. Because one thing I wanted to also mention is there are some other analogies or other models for general relativity.
Oh, hey, let's go back to that acceleration curve real quick.
Oh, okay, sure.
It looks a little funny to me. Oh no, I'm getting it because if we're on the left, the acceleration's to the right, positive, and if we're on the right, then
Oh,
acceleration
yeah.
is to the left, negative. Okay, yeah, that asymmetry threw me off for a
Oh,
second,
yeah, we
but it
could
makes
take the
perfect
absolute
sense.
value or
Yeah.
something, but would be more intuitive to have the absolute. Yeah, makes sense.
Well, I mean, it depends on what you mean by intuitive. So yeah, I mean, it's intuitive
Yeah.
now that I get it. Yeah.
I know
So,
there's some other models like the river model where, and it looks, I mean, the idea is nice. Basically, you map all of the math of general relativity to basically something that's space flowing into mass. And, I only have one small visualization for that. So you basically imagine the higher the gravitational, the more mass you have, the more space would flow into mass.
mhm.
And mathematically, it works out perfectly. There's absolutely no problem with that. My issue with this is the ontology because there are always
Mm.
questions. Well, if this were happening, well, where is that thing going? Where is it going? What's
Yeah.
the mechanism? Where's it coming from? Is it just disappearing? Again, what's the mechanism? What about conservation laws? Is as much going away as coming in? We have no model for that, right? And also the other
Yeah,
thing
is an
is
entity being created or annihilated in these situations? And
it makes it
we have
really even
no,
if this were possible, like it makes it really you need to have all these additional things to explain and model, right?
yeah,
And then also the conversation. And the other thing is because so it does explain it, but the thing is, when you think about this, if this inflow would cause space to get denser near massive objects, because if space is flowing in, by definition, it will get more dense. But that would also change the speed of light. So then you have to kind of do some accounting to make sure it's really fine-tuned that overall, the speed works out because now you have to consider the speed of light changing because of the refraction, because you're changing the density and the inflow, which makes it really difficult to model also. And the other thing is in the center of objects. So based on that model, right, in the center, if you were in the center of the Earth, there's no flow because when you're right in the middle, um, there's no space flowing towards you at that point. So the clock shouldn't run slower. They should just have the normal speed as they have outside. That's a clear contradiction to general relativity. Of course, that could be measured. I mean, so if people who think that's a valid model, they could do that experiment, right? Probably, and see if that works. Another thing I see is superluminal issues. So when you have space flowing in, like the sun we had before, the black hole, it would have to flow faster than the speed of light, right? Which is kind of weird because then the medium would flow faster than its wave speed. So I mean, that's why I'm not considering it because I want to, look at the simplest model first. And if that doesn't work out, I'm perfectly fine expanding and looking at other things. But this just makes it really
right. But
complicated.
yeah, the river model, it presumes that an entity is being annihilated and then created. So, and we've never seen an entity be annihilated or created. So that's a pretty, again,
Yeah.
we're talking about some kind of unprecedented, doesn't mean it's impossible, but it means
Yeah.
like there's some unprecedented physical like phenomena happening here where an entity is actually vanishing from existence, which by the way, that might be metaphysically impossible. There might be like some kind of argument that that violates the basic laws of existence.
Oh,
But
we could
I
fix it.
haven't quite
We
heard
could,
that.
what we could do, of course, yeah, well, there's a fifth dimension or a fourth, whatever. Let's say fifth dimension, and
It's
each
just
time
going
it's through in a
away.
loop, but then you have to have this extra dimension. It's like,
Yeah, you're just stacking more hypotheses at this point.
it is just you're adding stuff like the epicycles, and
Yeah,
that bothers me. Like I was just let's just too simple. Let's not invent time reversal or new dimensions.
yeah.
Let's see how far we get with that. And if needed, and if it's really strong evidence, of course, maybe this won't work out. And but anyway, so there's another one. I just want to briefly mention it because some people have
Well,
talked about.
actually, before
Oh,
we
okay.
move on, there's a few things I wanted to note. So, like,
Okay.
what the philosophical argument for what you're saying here is that the more, and Ron Pizzaturo covers this in his book, A Validation of Knowledge. He gives an explicit mathematical account of Occam's razor, basically,
Yeah.
which is the way he takes it to mean is the more hypotheses you introduce, the less likely it is to be true, all other things being equal. Because each hypothesis, you don't know if it's true. There's
Yeah.
some probability of it being true. And obviously, the more of these uncertain hypotheses you introduce, all other things being equal, which maybe they're not, maybe there's an argument for flowing
Yeah.
ether, but but all other things being equal, the more hypotheses you introduce, the less likely it is to be true. So the hypotheses that have less assumptions in them are more likely to be true. So I'm
I
on
think
board with you.
Einstein had this approach too, right? He said something like as simple as possible, but not simpler, or something like that.
Yeah, yeah, exactly.
That's what I
Now,
think too.
I
I mean, I like that.
yeah.
Yeah.
Now I also want to take this opportunity to explain why I'm so against calling it space instead of ether. So notice
Okay.
I insist on calling
Mhm.
flowing
Sure.
ether, not flowing space,
Okay.
because that in this case, we can see it's not a matter of what's the word, rhetoric. It's not a matter of rhetoric. It's a matter of physical clarity here.
Yeah.
Here's why.
Mhm.
When we say flowing space, what are we talking about? We're using the
Yeah.
word flowing. Flowing is a kind of moving. What is moving? Moving is
Mhm.
changing its location, changing its spatial relationships
Yes.
with
Yes.
respect to other things. So you're saying that
Mhm. Mhm.
space changes its spatial
Okay.
relationship to
Yeah. Yeah. I
other
see your
things.
point. Yeah.
So
Yeah. I get it.
you are now using the words in a way that makes it
Mm.
impossible to make progress, just like
Yes.
mainstream physics. This is the exact kinds of, and
Yeah.
they're like,
Yeah. Yeah.
doesn't
Hmm.
matter because we have fields, and there's a problem with that kind of argument. Like if you call it a field, fields mean something in particular. They just
Hmm.
talk about the potential for a particular kind of action to happen at any one location. So if you treat the fields as though they're the medium, then you miss out on
Hmm.
identifying the properties of the medium.
Yeah.
In
Makes
this
sense.
case,
Yeah.
if you treat space as though it's the same thing as the medium, then all the things that have to do with location and if something's moving, all of that just gets like packaged together and mixed up and
Yep. Yep.
confused
Hmm.
with the entity. There's an
Hmm.
entity here, so we have to call it a medium or a
Yes.
ether or a
Medium is
plenum.
fine. Yeah. I can live with the
Well,
medium.
yeah, yeah, whatever we need. Yeah, go
No,
ahead.
I totally agree with you. Yeah, yeah, I get your point because we are kind of confusing thing. We're calling space two different things. We're calling it, you know, the spatial distance, yet we're calling space something else as well. So yeah, it is confusing. We should probably use a different word for that. I agree.
Yeah, I
Yeah.
think we have to adhere to the word
Hmm. Hmm.
ether. Now, it's true rhetorically when you're trying to explain to people, it's true. You shouldn't use the word unless you're ready to explain the Michelson-Morley experiment and why
Yeah,
that
yeah.
didn't
I think
really
now we can
disprove the
call it ether
ether
because now we've
and
explained it, right? We have explained. I think it's
yeah.
safe now because we have explained what we mean, you know.
Yeah.
But when
Yeah.
you start with that, then it's like immediate blockage. So, but now I think
Yeah,
it's
that
okay. Yeah.
that's a rhetorical issue for
Yes,
how
yes.
we communicate the point to other people. But for our own clarity, we can't use the word space here because you get
Okay.
yourself into self-contradiction.
Okay,
So,
makes sense. Sounds
okay,
good.
cool. I'm glad we
Sounds
agree on
good.
that.
Sounds
So
good.
change
Okay.
this. Change this in your presentations. If you
Okay,
really
okay.
agree,
I'll call it
if you find an argument against me, just tell me in the next video and you can say, "Hey James, I kept the word space and here's why I kept it." And then we'll
okay.
discuss it then. But
Okay.
until then you got to change it. Otherwise
Okay,
it's
I'll
so
change it.
unclear.
I'll change it.
Okay.
How good. There's another one. I know this is like a
Okay.
kind of silly model, but I did look at this too. I just wanted to be, look at all the models. There's something called push gravity.
Mm.
And the idea is that there's like a hail of corpuscle, basically gravitons that are
Hmm.
flying in from all directions. And there's like
Hmm.
a shading effect. So when you have these things flying,
Mm.
it will push the matter more when you have other matter nearby. And actually I do have a simulation on that also. It's not great, but it's just some. So when you move them closer, overall, there's a shading effect, and the
Mm.
arrows more often go to the center. It's not perfect, but it
Well,
shows
but
the idea.
on
On
average,
average, you can
it
see the
is
arrows.
perfect,
Yeah, yeah.
basically. So what's going on? So tell me if I'm understanding this correctly. We got all these green particles just jiggling around everywhere, just bombarding the blue balls from every side.
Yeah,
But the blue balls are shading one another
yeah.
from the impacts of the green dots. And so in
Yes,
general, and so these red arrows indicate the force vectors at any one
yes.
instant. And you can see that in general, the force vectors tend to point towards each other. Why? Because there's more so let's focus on the left ball.
hmm
On the left ball, there's more impacts on its left, pushing it to
Yes,
the right, than there are impacts on the right. Why?
yeah.
Because the right ball's in the friggin' way. And so there's less impacts over
Exactly.
there. Yeah, and so this adds up to masses getting pushed into one another.
Yeah, exactly. And it's pretty
Yeah.
clever. But again, there are problems, of course, like why would clocks slow down? What about lensing? What about aberration? If we don't see any aberration, where are they coming from again? Why are they flying in a particular direction? So anyway, it's a nice model, but I don't think it works out. I didn't look more into this because I could see some issues right away, so I didn't pursue this any further. So to
Mm.
me, in summary, what we have to talk right now is basically a model where all we are saying is space. Well, the medium, what shall we call it now? The space, the medium of space, whatever you want to call it. There's an ether, so there's a medium and
Hmm.
it has properties of an elastic solid. And just from that alone, we get to refraction because as soon as you change the density or stiffness of this medium, you end up with refraction, which then can explain how matter gets attracted by other matter. You can see how light is bending. Um, and it's all pretty simple. I mean, refraction is very easy to understand. So we don't need any extra magical things. That's all we need is just saying there is a medium and it has the properties of an elastic solid. So in the next episode, now we're going to continue. Well, if that works out, well, how about special relativity? So why are moving clocks slower? And is there a way? Because often people think that when you assume there is a medium, then it can be detected. So we will think about that. Is there a way to detect it or maybe not? What are the challenges? And so with this, we end this episode.